To dive into a powerful way to describe motion on a flat surface. We'll be exploring parametric functions, modeling planar motion. Imagine watching an object, like a ball, moving through the air. You can't describe its path with a single function like y equals f of x, because at any given height, the ball could be at two different horizontal positions. To solve this, we can use a third variable, called a parameter. The most common and useful parameter is time, denoted by t. In this video, you will learn to describe planar motion using parametric functions, identify horizontal and vertical extrema of a particle's motion, and calculate its position at any given time. By the end, you'll be able to paint a complete picture of an object's journey. So, how do these parametric functions work? We use a set of equations to define a particle's position. A parametric function is written as f of t equals the ordered pair x of t, y of t. Here, x of t tells us the horizontal position of the particle at any given time t, and y of t tells us the vertical position at that same time. Think of it this way. For every single value of time t, these two functions, x of t and y of t, generate a single point, an xy coordinate, that represents the particle's location. As t changes, the particle moves, tracing out its path. Let's look at a concrete example to make this clearer. Suppose a particle's motion is described by these equations. Let's say x of t equals t squared, and y of t equals t. We'll examine the path for values of t from -2 to +2. Let's pick some time values and see where the particle is. We'll start with a table to organize our points. First, we create a table with columns for t, x of t, y of t, and the resulting ordered pair xy. Let's find the position at a few key times. First, at t equals -2. At t equals -2, x of -2 is -2 squared, which is 4, and y of -2 is simply -2, so the position is the point 4, -2. Now, let's try t equals 0. When t equals 0, x of 0 is 0 squared, which is 0, and y of 0 is 0. The particle is at the origin, 0, 0. And finally, let's see where it is, at t equals 2. At t equals 2, x of 2 is 2 squared, which is 4, and y of 2 is 2. The position is 4, 2. Now, if we plot these points on an xy coordinate plane and connect them, we get the path. But it's more than just a path. Because we have the time t, we also have direction. This shows the particle starting at 4, -2, moving through the origin at t equals sign 0, and ending at 4, 2. So, parametric functions give us a complete picture of motion. Our next objective is to find the horizontal and vertical extrema of a particle's motion. These are the points where the particle reaches its farthest to the right or left, or its highest or lowest point. We find horizontal extrema by identifying the maximum and minimum values of the x of t function, and we find vertical extrema by doing the same for the y of t function. Let's use our previous example. Remember the function? It was x of t equals t squared and y of t equals t for time t between -2 and 2. First, let's find the horizontal extrema. We need to find the maximum and minimum of x of t equals t squared on the interval t from -2 to 2. The function x of t equals t squared is a parabola that opens upwards. Its vertex is at t equals 0. The minimum value of this function on our interval is at the vertex. So, the minimum x value occurs at t equals 0, where x of 0 equals 0. The particle is closest to the y-axis here. The maximum value occurs at the endpoints of the interval. At t equals -2 and t equals 2, x of t equals 4. The particle reaches its farthest point to the right at these two times. Now let's find the vertical extrema. We need to find the maximum and minimum of y of t equals t on the interval t from -2 to 2. The function y of t equals t is a straight line with a slope of 1. For a continuous, monotonic function like this, on a closed interval, the extrema are simply at the endpoints. The minimum y value occurs at t equals -2, where y of -2 equals -2. This is the particle's lowest point. The maximum y value occurs at t equals 2, where y of 2 equals 2. This is the particle's highest point. By analyzing the individual functions x of t and y of t, we can determine the full range of motion. We now know our particle moves between an x value of 0 and 4, and a y value of -2 and 2. Finally, let's learn how to find the x and y intercepts of a particle's path. These are the points where the path crosses the coordinate axes. The logic is straightforward. A point is on the y-axis when its x-coordinate is 0, and it's on the x-axis when its y-coordinate is 0. Therefore, the y-intercepts occur when x of t equals 0, and the x-intercepts occur when y of t equals 0. Let's stick with our example. X of t equals t squared, and y of t equals t, for minus 2 is less than or equal to t is less than or equal to 2. Here are our equations again. First, let's find the y-intercepts. We need to set x of t equal to 0. Setting x of t equal to 0 gives us t squared equals 0, which means t equals 0. This is the time when the particle crosses the y-axis. But an intercept is a point, an xy coordinate. To find the y-coordinate at this time, we plug t equals sine 0 into y of t. At t equals 0, y of 0 equals 0. So the only y-intercept is the origin, 0, 0. Now, let's find the x-intercepts. We set y of t equal to 0. Setting y of t equal to 0 gives us t equals 0. This is the time when the particle crosses the x-axis. Again, we need the coordinates. We find the x-coordinate by plugging t equals sine 0 into x of t. At t equals 0, x of 0 equals 0 squared, which is 0. So the only x-intercept is also the origin, 0, 0. This confirms what we saw in the plot. The particle passes through the origin at time t equals sine 0, which means it crosses both axes at that single point. Let's work through one more comprehensive example to solidify these concepts. Suppose a particle's motion is given by x of t equals the cosine of t, and y of t equals the sine of t. We'll analyze this for all times t from 0 to 2 pi. First, let's sketch the graph by plotting some key points. We'll use our unit circle knowledge. Let's test t equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. At t equals 0, cosine is 1 and sine is 0. So the point is 1, 0. At t equals pi over 2, cosine is 0 and sine is 1. The point is 0, 1. At t equals pi, cosine is minus 1 and sine is 0. The point is minus 1, 0. At t equals 3 pi over 2, cosine is 0 and sine is minus 1. The point is 0, minus 1. And finally, at t equals 2 pi, cosine is 1 and sine is 0, bringing us back to the start at 1, 0. If we plot these points, we can see a familiar shape emerge. Connecting these points reveals that the particle traces out the unit circle, starting at 1, 0, and moving counterclockwise until it completes one full revolution at t equals 2 pi. Now that we have a visual, let's analyze the extrema and intercepts for our circular path. Again, the equations are x of t equals cosine t and y of t equals sine t for t between 0 and 2 pi. Here are our equations again. Let's find the horizontal extrema. We need the min and max values of x of t equals cosine t on the interval from 0 to 2 pi. The cosine function on this interval has a maximum value of 1, which occurs at t equals 0 and t equals 2 pi, at the point 1, 0. It has a minimum value of minus 1, which occurs at t equals pi, at the point minus 1, 0. These points correspond to the leftmost and rightmost points on our circle. The particle goes as far left as x equals negative 1 and as far right as x equals 1. Next, the vertical extrema. We need the min and max values of y of t equals sine t on the same interval. The sine function on this interval has a minimum value of minus 1, which occurs at t equals 3 pi over 2 at the point 0 minus 1. It has a maximum value of 1, which occurs at t equals pi over 2 at the point 0, 1. These points are the lowest and highest points on the circle. The particle goes as low as y equals negative 1 and as high as y equals 1. Now for the intercepts. First, the y-intercepts. We set x of t equal to 0. Since x of t is cosine t, we have cosine t equals 0. The solutions in our interval are t equals pi over 2 and t equals 3 pi over 2. At t equals pi over 2, the point is 0, 1. At t equals 3 pi over 2, the point is 0, minus 1. These are the 2 points where the circle crosses the y-axis. Finally, the x-intercepts. We set y of t equal to 0. Since y of t is sine t, we have sine t equals 0. The solutions in our interval are t equals 0, pi, and 2 pi. At t equals 0, or 2 pi, the point is 1, 0. At t equals pi, the point is minus 1, 0. These are the 2 points where the circle crosses the x-axis. Notice that at t equals sine 0 and t equals sine 2 pi, the particle is at the same x-intercept, but at different times. So, let's recap what we've learned today. We've introduced parametric functions as a powerful tool to describe planar motion. We saw that a function of time, f of t equals x of t, y of t, gives us a particle's position on a plane. The graph of this function shows the particle's path and its direction. We learned how to find the extrema of the motion by simply finding the min and max values of the x of t and y of t functions separately. And we discovered a straightforward method for finding intercepts. Y-intercepts occur when x of t is 0, and x-intercepts occur when y of t is 0. We've met all of our learning objectives. You can now describe planar motion and use the functions to pinpoint the most extreme locations and axis crossings. Understanding these characteristics is the first step toward analyzing complex motions in the plane.